Hello, everybody. So today we're finishing in this video, we're finishing the last topic of our second chapter that discusses computability and decidability. And this is Kolmogorov Complexity. I think it's a fun topic. I like it. And although it's probably be a little bit confusing at first, but hopefully you can get a hang of it. So after some of the previous videos that required a lot of effort, I thought I'll reward you with a short segment of a movie that I seriously recommend, Rosencrantz and Guildenstern Are Dead by Tom Stoppard. I recommend the entire movie, but for this class, let's see a segment.
Heads. 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 Heads I win. Again. Heads. 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 Whoops. It must be indicative of something besides the redistribution of wealth.
So I hope you enjoyed this short lesson in probability and physics and economics and a lot of other stuff. And again, I'm recommending this movie. But let's consider another example, a simpler example. And imagine that there is a lottery in a small village, and the winning numbers are 1, 2, 3, 4, 5, and 6. Furthermore, perhaps the winner is one of the village crooks. So something is really suspicious here. On the other hand, the probability of getting the numbers 1, 2, 3, 4, 5, 6 is just as likely as getting any other 6 numbers like 4, 12, 22, 29, 34, 47. So why are we so suspicious when we see one sequence, but completely oblivious when we see another sequence? Why are we surprised at 80 heads, rather than it head to tails, another head, another tail, and so on, both of these sequences have the same probability. So the church-Turing thesis, which we discussed a few times, tries to give a universal notion of computation. Everything that could be computed by a Turing machine. That's the thesis, that's the hypothesis. So it's a universal theory of computation. And with Kolmogorov complexity, we want a universal theory of information. Can we quantify how much information is contained in a string? Is the information in 1, 2, 3, 4, 5, 6 different than the information in a different sequence? If we have here two sequences, perhaps one A looks less random. How can we formalize that? And the idea is that the more we can compress a string, the less information it contains. That's the philosophy. So let's define it. This is the amount of information in a string. X is the length of its shortest description, how much we can compress it. How can we describe a string? So if we want to talk about shortest description, we need to say what is a description. And we are going to, not surprisingly, use Turing machines for that. It's a class on computability. So if X is any string, we can say that a description of X is a string MW, such that M on input W halts with only X on its tape. So this is a computation that computes X. If you give me M and W, I can simulate this computation and get X. The shortest description of X, which we'll denote by D of X, is the lexicographically shortest string MW, such that M of X halts with only X on its tape. Since our descriptions are pairs MW, it will be convenient for us to, or we'll actually need a way to encode a pair. And we actually already discussed encoding pairs, encoding a comma, when we discussed encoding Turing machines. And here we'll discuss a particular way of encoding a function that will define as this brackets and a comma inside that takes two strings and produces a single string. And we have decoding pi1 and pi2 such that if Z is the encoding, this combination, this pairing of M and W, and it is if and only if when you decode Z with pi1 you get M, and with pi2 you get W. So it's a way to encode the pair in a way, one-to-one encoding that can be decoded. More specifically, we will consider the following pairing that takes MW and then encodes it as 0 to the M, to the length of M, a single one, M and W. So we discussed in the past two ways of encoding. This one is more efficient when one of the string is small. In our case, M is a constant, it's a Turing machine, W will be longer, so we don't mind being a bit more wasteful in our encoding of M than in our encoding of W. So with the zeros and 1, we indicate what's the length of M. And then after that, we know that we have MW, and we know exactly the length of M, so we can break MW to M and W. So if we want to encode 10110 the first string is of length 5, so we'll have 5 zeros and a 1, and then we will just have the concatenation of the first string and the second string. Note that the length of this encoding is twice the length of M, or of the first string, plus the length of the second string, plus 1. This is kind of a low-level technical detail, but it will be useful for us. So, Kolmogorov complexity. The shortest description of X is denoted by D of X. And the Kolmogorov complexity of X, denoted by K of X, is the length of the shortest description. And we'll start with a few examples that will kind of give us some of the extreme points about Kolmogorov complexity, and we'll explore more properties later. So the first thing we want to say is that the Kolmogorov complexity of a string cannot be much longer than its length. We can think about it as the length of a description. The string itself, in a sense, it's kind of a description, and I want to say that the way we define descriptions here doesn't cost us much more. So most formally, there is a constant C, such that for all X, for every string X, the Kolmogorov complexity of X is at most the length of X plus C. The amount of information in X isn't much more than its length. And so define a Turing machine, very simple one, that on input W just halts. So this Turing machine just outputs its input. And on any string X, M of X halts with X on its tape, and therefore M, the special machine M, comma X, is a description of X, and its length, by the pairing we discussed before, is twice the length of M, plus 1, which is C, plus X itself. So the Kolmogorov complexity of X is this length, which is twice M plus the length of X plus 1, which is the length of X plus C. So, so this shows the first property. The Kolmogorov complexity is kind of bounded more or less by the length of a string. But there are strings with much lower Kolmogorov complexity. And one way of getting them is by repetition. If you repeat a string, then the Kolmogorov complexity doesn't increase as much. So there is a fixed constant C, so that for every n larger or equal to, and every x every string x, the Kolmogorov complexity of x to the n, which we mean x concatenated to itself n times, is at most the Kolmogorov complexity of x plus c log n. So the information in x to the n isn't much more than in x. It goes larger logarithmically in n rather than multiplicatively in n. So the way we do it, we define a Turing machine n that on input, which its first ingredient is an integer n, and its second ingredient is a pair mw. First compute x, which is m of w, and then prints x n times. So you can believe us and kind of confirm that you can do that in a Turing machine. You can imagine the pseudocode, it's not hard. And n is a Turing machine of some constant size. So given this machine n, let's see how to encode the string x to the n. And for that, we want mw to be not any M and W such that compute X, but actually be the shortest description of X. And then the Kolmogorov complexity of X to the N is at most the description length of this string N, comma, big N, comma, small n, comma, this per MW. Because N on this input will write X N times. And now we only need to kind of count the length. And for counting the length, what's important is this notion that when we encode pairs, we encode it in a way that preserves the length of the second string and multiply by 2 the length of the first string. And that would mean that the length of this description is 2 times the length of n, which is a constant, plus some other constant times log n, plus the Kolmogorov complexity of X, which is the description of MW, which is at most C times log n plus the description length of X for some constant C and D, and we're done. So if you're repeating a string n times, essentially all you need to tell me is how to describe this string once, and then how many times to repeat it. So for the string 0, 1, 0, 1, 0, 1, that we had an intuition that it is a simple string, or more formally for the string 0, 1 to the n, we know that the Kolmogorov complexity of it is going to be logarithmic because you need the Kolmogorov complexity of the string 0, 1, which is a constant, because its length is a constant, plus C times log n. So for every n, the Kolmogorov complexity of this string is at most D plus C log n for some constants. Okay, so we saw two extremes. We saw an extreme where, so we saw that on one hand, the Kolmogorov complexity of every string is bounded by n more or less, and we saw a string that has Kolmogorov complexity, which is essentially logarithmic. And now we want to see, before we kind of move forward with understanding this model, we want to ask ourselves, did we marry ourselves to this computational model of Turing machines, and how much does it tell us in general? Perhaps there is a different way, using some other machine model, for example, some programming language like C++. I'm old-fashioned this way, and perhaps we will have significantly shorter descriptions with this other programming language. So for that, let's consider this notion of an interpreter, like an interpreter of a language, which is a semi-computable function, P, from strings to string. And essentially, it takes a program as input and may print its output. So for example, for a Turing machine, you can have, once you take a machine, you can simulate it, like in a universal Turing machine, and if the machine halts, then you're going to print its output. So given any interpreter, we can define now a new description length, which will give us a new notion of Kolmogorov complexity. So let X be a string. The shortest description of X under P is called dP of X. Is the lexicographically shortest string W, for which P of W equals X. So P perhaps is the interpreter for C++. And now we can define the Kolmogorov complexity under P, so Kp of x to be the length of the shortest description under P of x. The theorem is that this doesn't matter much. For every interpreter P, there is a fixed C, so that for every string, the Kolmogorov complexity of x is at most the Kolmogorov complexity under P of x plus C. So there isn't a smart way to come up with a different language that would change dramatically the Kolmogorov complexity of strings. So using another programming language would only change this Kolmogorov complexity by an additive constant. And this is kind of an universal notion of compressibility. The proof is that we can define M such that on W, it simulates P of W, right? It's a computable function, and we can simulate its computation and write its output on, to the tape. Then M and the description dp of x is a description of x under the standard Kolmogorov complexity notions. So the Kolmogorov complexity of x is the length of the description m comma dp of x, which is twice the length of m plus the Kolmogorov complexity under p of x plus 1, which is at most a constant plus the Kolmogorov complexity under p of x. Not very surprising. So what do we know? We know that there are strings that have very low Kolmogorov complexity, logarithmic. We know that the maximal Kolmogorov complexity is essentially n, essentially the length of the string, perhaps plus a constant. And we know that that doesn't matter what programming language we're using. Now we'll see that this upper bound of essentially n is pretty tight. So the theorem is that for every n, there is a string x that requires n bits to represent. So k of x is at least n. There are incompressible strings of every length. So it cannot be the case that all strings are going to have this logarithmic description length. The proof is just by counting. The number of binary strings of length n is 2 to the n, but the number of descriptions of length shorter than n is bounded by the number of binary strings of lengths shorter than n, which is 1 for the empty string plus 2 for strings of length 1 and so on. And this will be 2 to the n minus 1. So there are less descriptions. If we only consider description of lengths smaller than n, there are less descriptions than strings that we want to describe. And there must be, therefore, because every description describes a single string, there must be a string x that doesn't have a description smaller than n. So there is an incompressible string for every length. In fact, there are many incompressible strings for every length, and a random string will be incompressible, and the probabilities depend on how much you want to compress it. So for all n and c, which is larger or equal than 1, the probability that a random string of length n will have Kolmogorov complexity at least n minus c is at least 1 minus 1 over 2 to the c. Put differently, the probability you get descriptions that are shorter than n minus c is at most 1 over 2 to the c. And so for large C, this is going to be very low. Most strings are highly incompressible. You cannot save more than a constant number of bits. And that's exactly the same argument. The number of binary strings of length n is 2 to the n, but the number of descriptions of length smaller than n minus c is at most the number of binary strings of this length. I mean, not necessarily every binary string would give us a different description, but yet, and this is at most 2 to the n minus c minus 1, which gives us the theorem that we wanted. Because the number, again, every description describes a single string, so the probability, so there are at most 2 to the n minus c minus 1 strings that have these short descriptions, and the probability of hitting one of them is that over 2 to the c, which is smaller than 1 over 2 to the c. You can confirm the algebra. So what do we know? Again, we know that there are strings with logarithmic description. No string has more than linear description length. Most strings are actually incompressible. So now the natural question is to answer or to find what is the best way to describe a string. Which strings have low complexity and which don't? And let's look at these three examples. And this is a good place to pause the video and ask yourself for each one of them, do you see a way to describe this string in a short manner? And what would be that? So hopefully you paused me and now you're back. And let's see. For the first string, if we partition it correctly, we can see that this is the concatenation in lexicographic order of the first strings. So 0, 1, 0, 0, 0, 1, all the way to 0, 0, 0, 0. What about the second one? If we break it correctly, we see that it is a Fibonacci sequence. So 1 plus 2 is 3, and 2 plus 3 is 5, and 3 plus 5 is 8. And you know the drill. What about the third one? It's maybe a little bit more confusing. So you have 1, and 1 times 2 is 2. 2 times 3 is 6. 6 times 4 is 24. 24 times 5 is 120, and so on. So the nth number is n times the n minus 1 number. So that's nice. I hope you got some of them, but you can see that it's not easy to decide which strings are compressible and which are not. And in fact, this is not a coincidence. It's not only you. It's really hard. So consider this language, KXC, such that the Kolmogorov complexity of X is at most C. Is there a way to compute it? Is this language decidable? Turns out that this language is undecidable. We could have started our notion of undecidability, the concrete problem, from compress rather than from ATM. So here is the idea. If this is decidable, then we can design an algorithm that prints the lexicographically first incompressible string of length n. Okay, let's parse it. If it's decidable, there is a machine that decides it. And now we can go over in lexicographic order over all the strings of length n, and see, can check for each one of them if it's compressible or not, and output the first one that is not compressible. But the point is that such a string could be succinctly described just by providing this algorithm code that does this this enumeration, and n in binary, n is logarithmically long. So this machine that takes n in binary and outputs the first incompressible string of length n will produce something that is actually compressible, and that's going to be a contradiction. This is a little bit similar or very similar to Berry paradox that asks for the smallest integer that cannot be defined in less than 13 words. But the problem is that the smallest integer that cannot be defined in less than 13 words is a sentence with less than 13 words. So this number contradicts itself. The smallest integer that cannot be defined in less than 13 words is definable in less than 13 words. This is the paradox. The issue is that it's not a valid definition, and you can think about what we saw here as a way to formalize it. So this was an intuition, and now let's formalize this proof that compress is undecidable. So compress, we said, is pairs of string xc such that the Kolmogorov complexity of x is at most c. We want to say that it is undecidable, and suppose it is decidable. For the sake of contradiction, consider the Turing machine M that on input x, which is a string, defines n, which is just 2 to the length of x. So x defined to us n, but just in a very sparse way. And now it goes over all strings y in lexicographical order and checks that yn is not incompress, meaning that y doesn't have a description of length smaller than n. This means that it will force us to look at strings that are long, because every string that's much shorter than n will definitely be incompress. And then it prints y and halts. So it prints a y, which is the first string in lexicographic order that cannot be described. Its description length is larger than n. So m of x prints the shortest string y prime such that the Kolmogorov complexity of y prime is larger than 2 to the x. But because m prints x, because m prints y prime, then m comma x is a description of y prime. The length of this description is m, is the length of mx, description of mx, which is a constant plus the length of x. And the length of x is logarithmic in n, which will create a contradiction. So the length of the Kolmogorov complexity of y prime is larger than 2 to the length of x, but it is also smaller, equal than d plus the length of x. And for every x that is a little bit large, this is a contradiction. So compress cannot be decidable. And now if we started our discussion of undecidability with compress, we could quickly get to prove that ATM is undecidable just by a reduction. So we can reduce compress to ATM and get our last proof, I think, in this class, that ATM is undecidable. Given a pair XC, our reduction constructs a Turing machine. So you need Right, XC is the input for compress. You need now an input for ATM. So the first part of it is going to be MXC, which on input W. For all pairs M prime, double prime, with a description length smaller than C, simulates each M prime on W prime in parallel. And if some M prime halts and prints X, then it accepts. First, what does it mean that you simulate all of these M primes on W prime in parallel? You can simulate one machine for one step, and then kind of go all over them for one step, and then try on two steps, etc. As long as, and the moment you find one description of X with at most C bits, which is what we do here, you're going to halt and accept. So what do we have here? For MXC to accept the empty string, or any string, MXC ignores its string. What do you need? You need that there will be some description of length at most C of X, meaning that the Kolmogorov complexity of X is at most C. On the other hand, if there is, if the Kolmogorov complexity is larger than C, then there will be no such description, and MXC will not accept epsilon. So the reduction from the pair XC as input to compress to the pair MXC epsilon is a reduction from compress to ATM. Okay, so what do we have? So far, we talked about Kolmogorov complexity, some of its properties. We connected it to this notion of undecidability, and we showed how we could have started our discussion with the Kolmogorov complexity. And now let's connect it to the previous topic that we discussed, which is interesting formal systems. And we defined the formal system to be interesting if any mathematical statement that is describable in English could be described in this system. Proofs are convincing, and if there is a proof that you can describe in English, then you can also describe it in this system. And we, as you see here, we kind of, as a reminder, we formalized all of those properties using the language of computation. We wanted the statements that M accepts W to be in the language, to be expressible in F in this system. We wanted the language of statements and proofs to be decidable. And we wanted proofs for the statements that M accept W, because there are proofs in standard language, which is just the computational path of M that accept W. So this is a quick reminder. You can look at the previous video again. So we proved that there are, so in every interesting and consistent F, there are unprovable statements. And here we're going to give a different unprovable statement. Again, a very interesting statement that is unprovable. And this is, so we're going to show that for every interesting consistent F, there exists a T. So for some large enough T, and for any string X, the statement that the Kolmogorov complexity of X is larger than T is unprovable in F. And let's prove it. So define an M that treats its input as an integer. So m and m on k, so if its input is an integer, let's say that it's k, it searches over all strings x and proofs p for a proof in f that the Kolmogorov complexity of x is larger than k. And you're going to output x if found. So you're enumerating all strings x and all proofs in some lexicographic fashion from short to large. And the moment you find any proof for any x that the Kolmogorov complexity of x is larger than k, you're going to output x if it's found. And suppose m of k halts, then it is going to print some x prime, right? When it halts, it's going to output some string. That's how we define this machine m. So the Kolmogorov complexity of this string that we're going to print, x prime, is at most the Kolmogorov complexity of this pair, m, comma k, which is at most c for describing m, plus the length of k. But the length of k in binary is logarithmic, so it is at most c plus log k. So what we know is that the Kolmogorov complexity of x prime is at most c plus log k for some constant c. But remember, what was this x prime? This x prime was some string for which we found a proof that the Kolmogorov complexity of x prime is larger than k. And f is consistent. So therefore, the Kolmogorov complexity of x prime is indeed larger than k. If you have a proof, then it is true. So what we get here is that the Kolmogorov complexity is larger than k, but smaller than c plus log k. And this will create a contradiction because when k becomes large, this is impossible. Because k is smaller than c plus log k only for small enough k's. For large k, k is larger than c plus log k. So if we choose t to be greater than this kind of k's, then we get a contradiction. So what it means is that m on input t cannot halt. And this means that it cannot halt. It means that it cannot find a proof for any string that k of x larger than t. So this is what we wanted to show is that for some t large enough, and for any x, there is no proof in this formal language that k of x is larger than t. Again, an interesting statement in this formal language that cannot be proved. But if we're looking at that, what we get actually, is not only that there is one unprovable statement, but actually that there are many unprovable statements, and that a random statement is going to be unprovable in a sense. There is a distribution on statements which almost all of them are correct and none of them have a proof. For every interesting consistent f, there is a t such that for all x, you cannot prove k of x larger than t. That's what we proved in the previous slide. But for a randomly chosen x of length that is large enough, like t plus 100, for almost every such x, its Kolmogorov complexity is larger than t. K of x is larger than t with probability at least 1 minus 1 over 2 to the 100. So overwhelmingly right. So we can, with very high probability, produce a statement which is correct, but has no proof. If I just select X at random, and I write down this statement, it's very, very likely that it is true, but it's unlikely to have a proof. Oh, sorry, it doesn't have a proof. So kind of rephrasing it, for every interesting formal system F, there is always some finite integer so that you'll never be able to prove in F that a random large bit string requires a much shorter bit program, although it's extremely likely to be correct. The chance that it's incorrect is less than everything we believe in collapsing at once. So kind of as parting thoughts, Kolmogorov complexity is a universal theory of data compression. This is an opportunity for me to tie this back to the story from the beginning. What we had stories in the beginning of strings that look to us not random. So the lottery gave us 1, 2, 3, 4, 5, 6, and we felt that something is fishy here. And on the other hand, we knew that the probability of 1, 2, 3, 4, 5, 6 is the same as the probability of any other string. So it wasn't clear what's the basis of our skepticism. And one way of formalizing it is that it's true, every string is as likely as any other string. But given what we saw in this video, the strings with small Kolmogorov complexity, like 1, 2, 3, 4, 5, 6, that have a very small Kolmogorov complexity, these strings it's a very small group. We saw that almost all strings have complete Kolmogorov complexity. So a priori, if you ask me today, what's the probability that we will have in the lottery any string with small Kolmogorov complexity, this probability is going to be very small. And therefore, when we see such a string, we should worry. Similarly with the sequence of bits of heads, of 80 heads, this is extremely unlikely because it has very small Kolmogorov complexity. And a priori, we know that we will fall in a string with very small Kolmogorov complexity with a very small probability. So it's a very interesting theory. It is universal in the sense that using Turing machines doesn't seem at the moment to limit us unless we find that the Church-Turing thesis is incorrect. There are algorithms that cannot be captured by a Turing machine. And we saw that it kind of ties back to things that we care about, like undecidability and the foundation of math. And therefore, it is really a nice place to finish the second chapter of this class that talks about undecidability and Turing machines. And we will start discussing a topic that's close to my heart, which is computational complexity. Thank you.